So we already addressed this problem with a point dipole in free space. We were able to exactly calculate the Green's tensor of the point dipole. Using that Green's tensor, we calculated the distribution of electric and magnetic fields. That allowed us to calculate the Poynting vector. And then by integrating the Poynting vector over the entire sphere surrounding the dipole, we calculated the total energy flux carried away from the dipole. And in principle, we could do basically the same thing. In this case, given any structure, we could try to find the Green's tensor, calculate electric magnetic fields, and then calculate the Poynting vector and integrate it. But turns out there's a simple approach. If, as long as we are not interested in precise angular distribution of the fields, and we are only interested in the emission intensity, there's a simpler way to find that emission intensity. And that way is offered us by the Poynting theorem. So the Poynting theorem says that if we surround the dipole by an imaginary sphere, only the dipole, without any structures, only the dipole, only the point source, we surround it by some, we enclose it by a surface dV. Then from the Poynting theorem, the emission intensity of this dipole plus this product of electric fields times current equals 0, which means that the emission intensity of a point dipole can be calculated as the imaginary part of the product of the dipole moment times the radiated fields at the origin. So what we need to know in order to find the total emission intensity is this guy, because the dipole moment is fixed, it is determined, it is related to the current. So what we need to find is the electric fields only at the origin. We don't need to find electric and magnetic fields here at every point in space and at every point at the integration surface. We only need this guy. Knowledge of this thing allows us to calculate the total emission intensity. And if we now express the electric field via the Green's tensor of the source, and we combine the different terms into p squared, then we obtain this simple expression, which says that the emission intensity of a point dipole can be expressed as a product of the magnitude of the point dipole and the imaginary part of the Green tensor at the origin, at the location of the dipole. We assume for the moment that the dipole is located at the origin of our Cartesian system. And also notice that the Green's tensor on both sides is multiplied. We take the scalar, the dot products of Green tensor with n, where n is the unit vector in the direction of the dipole. So P equals P times n. This is the unit vector in the direction of the dipole. It can be, if the dipole is linearly polarized, then n also is linearly polarized, but the dipole can be circularly polarized or elliptically polarized, then n will have the corresponding structure. So this is a very remarkable result. So we were able to calculate total emission intensity of a source in any environment without actually calculating the fields. We were able to express this quantity only as a function of the Green's tensor at the origin. So which means that once we know the Green's tensor, we immediately can calculate emission intensity and spontaneous emission decay rate of any dipole. So let us for a second look at the structure of this expression in more details. So the total field at the origin can be split into two contributions. The first contribution is the free space, so the primary field of the dipole. So that's the field that the dipole creates if we forget about the object, if we forget about the environment and assume that the dipole is placed in free space with epsilon equals mu equals 1. This is the primary field, E0 or E0. And this field is described by the Green's tensor that we calculated with you already 2 weeks ago. And that if we correspondingly calculate the emission intensity, we're going to obtain the Larmor formula, which describes emission intensity of point electric and magnetic dipoles in free space. But now we need to bring back the environment, our inhomogeneous objects, nanoparticles, surfaces, etc. And they are going to modify the Green's tensor, because what they're going to do is that the dipole is going to act with some fields on the environment. It's going to induce currents and polarizations in the objects, in the environment. And this polarization is going to produce an additional scattered field that is going to reach back to the dipole. And this is going to produce the additional scattered component at the position of the dipole. And so the total field is going to be the sum of these two components, the primary plus the scattered. And the sum of these two fields will determine the total field experienced by the dipole here. And this field acting on the dipole will actually perform work on the dipole. It's vice versa. It's the dipole that, so the dipole, the combination of charges, plus and minus, it performs work on the electric field, right? So it's some work, it does work. And this energy leaves the radiating system, and the radiating system loses the energy. So the dipole does work on the total field, and this is how it produces electromagnetic radiation, electromagnetic energy, and this energy leaves the radiating system at the speed of light. And so now you can notice that this emission intensity, the total emission intensity, is described by the imaginary part of the Green tensor. And for free space, you may recall that the Green's tensor has a singularity at the origin. The Green's tensor becomes infinite when we calculate the Green's tensor at the location of the dipole itself. And so you may think that the imaginary part will be infinite, but that's not the case. It is only the real part of the Green's tensor that diverges at the origin. And this is guaranteed as long as your dipole, as long as your source is located away outside any absorbed media. And only the imaginary part at the same time will be finite as long as your dipole is located in transparent medium. Of course, there will be difficulty. You're gonna face a difficulty when you place a dipole into an absorbent medium. For example, if you have some medium with epsilon double prime greater than 0, and you place a point dipole here, then imaginary part of the Green's tensor will also diverge, and that's not a very nice thing, which may suggest that the emission intensity becomes infinite, but that's not true in reality, because in any real physical system, the dipole has any source of radiation has kind of a finite size. And at that point, we need to consider the discrete structure of matter surrounding the dipole. And so in this case, the atoms or molecules absorbing bits of matter that constitute this absorbing material, they will be located only at a finite non-zero distance away from the dipole. And so this thing, although technically the imaginary part will be infinite, the absorption rate will not be infinite, because by assuming that there is a finite distance between the source and absorbing pieces of matter, we're going to avoid singularity. But this is a very technical matter, and to do that properly, you need to introduce non-local description of matter, which is far, far beyond the scope of our course. Now I just want to mention that you need to be careful with using the imaginary part of the Green's tensor for calculating emission intensity, and you can use that safely in any transparent medium. If your dipole is located inside an absorbed medium, then you might want to be more accurate. So let us write that expression, the final expression for the total emission intensity once again. And the quantity on the right-hand side of this expression plays a very important role in many areas of optics, nanophotonics, and quantum optics, and it is called the local density of state. To be specific, in this case, it is projected local electric density of states, all DOS for short. And it is given by the following expression. It does not have the point dipole, it is only the part of this expression that depends on the frequency and on the Green's tensor and on the direction of the dipole, on the unit vector n that describes the direction of our source. So why is it, first of all, why is it electric? Because we are dealing with electric dipole and we are dealing with electric Green's tensor. And you might remember that we can also introduce magnetic Green's tensor, which describes magnetic field produced by point magnetic dipole. Why is it projected? Well, because this Green's tensor gets projected onto our unit vector n. And so we do not calculate the full density of states, we calculate the projection of this thing onto the direction given, determined by our source that we are considering at the moment. So now why is the density of states? Why is it DOS? What is density of states? I forgot to mention that you can also introduce in a similar way the magnetic local density of states, in which you're going to have magnetic Green's tensor instead of the electric. So it's just a symmetric counterpart of the electric density of states. So now, what actually is density of states? Why is it so important in nanophotonics and quantum optics? Well, let us start with the usual density of states, not projected, not local, just density of states. And let us recall what it is. And you might have come across this quantity already in quantum mechanics, in classical electromagnetics many times. So density of state and in thermodynamics too. So density of state tells you if you have a configuration space of some modes, for example, free space electromagnetic modes propagating free space, or modes of a waveguide or something else. Density of state tells you how many states you have in a given system per unit frequency interval. And this can be visualized in a very simple, primitive way for electromagnetic modes of free space. Electromagnetic modes of free space are transverse plane waves that propagate in all possible directions. And for the sake of visualization, I illustrated here a two-dimensional k-space described by wave vectors kx, ky, and each mode is described by a dot, by circle, and each mode occupies certain phase space in this configuration space. And by counting all the modes with all different frequencies and wave vectors, we can calculate how many modes we have per unit frequency interval. And I'm sure you've done this exercise already in statistical mechanics classes and maybe in quantum mechanics, when you counted all electromagnetic modes of free space. And if you count modes in such a way, this is going to give you the just total density of states without being local, without being projected. And yeah, of course, this density of states, it changes depending on the environment. For example, if instead of considering all propagating modes in free space, you consider modes propagating through some dispersive material, through some resonant media or some waveguides with a cutoff, you're going to obtain a very inhomogeneous, in terms of frequency, density of states that's going to have peaks and troughs. So that's total density of states. Now, what is local density of states? Imagine that you want to weigh contribution of every mode of every state by the local electric field intensity. So let's say we have a certain structure, certain resonator, something like this. And I specifically draw that little appendix here, little pertursion. And we can we can solve Maxwell equations for this resonator bounded by perfect electric conductor walls, and we can find the eigenmodes of this structure. And these eigenmodes, they're going to have certain electric field distribution. Okay, and let's say we want to know not only the total density of states, how many modes we have in a certain frequency interval, but we want to know how tightly these modes are focused, how they are present in a particular point of our structure. And let's say this is our observation point, and we want to know the density of states at this particular point. And so by weighing all the modes, all these delta functions, by the local electric field intensity, we can obtain the local density of states, which tells you the extent to which all these eigenmodes are present here. For example, if we have a certain eigenmode that circulates just here along the bigger part of the system, but doesn't extend here to this little appendix, then density of states is going to be low. Maybe the total density of states is high for this system, but if the modes do not extend in this little part of the system, then local density of states will be very, very low. And this might be important in problems where you study interaction of light with point sources. And this is, by the way, why local density of states already appeared in the previous expressions, which describe emission density of a dipole into free space modes. So now you can start understanding why it is the local density of state that is important in description of emission density, because we want to know how strongly the modes of the system are present in a given point, for example, where we have a dipole, a point dipole source. So this is local density of states. Now, in order to introduce projected local density of states, we're going to modify this once again, and instead of just weighing these delta functions by local electric field intensity, we're going to weigh them by the projection of the electric fields onto some unit vector. That can be absolutely arbitrary unit vector, but on the previous slide, where we were discussing the emission intensity, that unit vector was the projection, the direction of the electric dipole. So this is the concept of the local density of states and how we go from density of states to local density of states to the projected local density of states by modifying the expression. And one can show that this local density of states that is introduced by the following expression, simply by counting all the modes and weighing them with the local electric field intensity, is absolutely equivalent to the following expression that we introduced earlier via the Green's tensor. And I'm not going to prove this today, but if you're interested, the proof of that equivalence can be done using the Green's tensor expansion over eigenmodes that we introduced in lecture 2. So a straightforward way to verify this is to plug this here into the expression for the density of states, expand, calculate the trace, imaginary part, expand all this crazy sum, and in the end you're gonna obtain just this. And this derivation, if you're interested, is done in Principles of Nano-Optics by Novotny. So the point is these two definitions of the local density of states are absolutely equivalent to each other. Now, one particular case for the density of states, free space. Let's find out what are the values of density of states in free space. In free space, we can immediately calculate the imaginary part of the Green's tensor at the origin, and it is gonna be this k over 6 pi times the unit diet, because this is still a tensor, and imaginary part still should be a tensor. And this is the unity 3x3 matrix. And by plugging this into the expression for the density of states, we obtain the projected loss in free space, which equals omega squared over this combination of constants. And of course, in vacuum, electric and magnetic density of states are equal because vacuum is absolutely dual with respect to flipping electric and magnetic fields. And so electric and magnetic local density of states are equal in vacuum. And these projected density of states are also identical for any direction of the unit vector because of the isotropy of vacuum. No matter in what direction you look, no matter in onto what direction you project density of states, of course, you should obtain absolutely the same result no matter how you look. And now if you calculate the full local density of states, not projected, but full local density of states, simply by counting the modes and projecting them, we will obtain this, which is just 3 times this expression, which makes sense because if we have full local density of states, we can project it onto 3 possible directions, x, y, z. And of course, the total density of states should be just the sum of all 3 projected ones, which are equal because of the isotropy, and we obtain this result. And this is absolutely the same result that you could obtain by counting the modes as you did in quantum mechanics and statistical mechanics, simply by assigning an elementary phase volume to each circle on the diagram, by counting all the modes that occupy a surface in the spherical space, just like this. And then by calculating how many states you have per unit frequency interval. So an exercise for you using the expression for the Green's tensor that we obtained 2 weeks ago, calculate the value of the imaginary part at the origin. This shouldn't be difficult. That's a useful exercise. Okay, so what can we do with the density of states? Can we introduce any useful identities and other useful expressions using this concept? Yes, one very useful quantity that we can introduce is the so-called Purcell factor. So let us write once again expression for the emission intensity of a point dipole in an arbitrary environment. For example, consider some quantum emitter point dipole located close to a nano-antenna, to a nano-resonator, anything. And let us, using this expression, let us calculate the resulting emission intensity of the dipole. And now the ratio of that emission intensity to the ratio of the same dipole in free space is called the Purcell factor. So we calculate this. Interesting. We calculate this. Then for the same dipole, for the same magnitude of P, we calculate emission of the dipole into free space, which we already know. And then this ratio gives us the Purcell factor, which shows the amplification of emission intensity due to the environment. It can be amplification, it can be inhibition. In some cases, spontaneous emission indeed can be inhibited. And if we express this Purcell factor through the Green's tensor of this given environment, we obtain the following very simple expression. So the extent to which emission rate can be enhanced or inhibited in a given environment is fully described by the frequency and imaginary part of the Green tensor at the origin, or the density of states alternatively. And we're going to talk a bit more about Purcell factor at the end of this class. Now I want to talk a bit more about what spontaneous emission is and a bit more about density of states in general. So this formula that is written here describes the enhancement or inhibition of spontaneous emission rate. Let's say that our point source that we are considering is in reality a molecule or an atom or some organic dye, quantum dots, an exciton, something that has two excited states. It has the grounded state and it has an excited state. And the molecule, the two-level system, is initially prepared in the excited state. And then, because this thing interacts with vacuum fluctuations of the surrounding environment, it wants to decay to the ground states with the lowest energy. And that process happens at a certain rate, gamma. Okay, and Fermi rule that you know from quantum mechanics actually tells us that the rates of this transition is described by the density of states, by the electromagnetic density of states. And this is exactly the same electromagnetic density of states that we just introduced moments ago, okay? And so the Purcell factor, which we calculated in this way for a classical dipole, for just a classical monochromatic antenna, in the case when we are considering a quantum emitter, which is prepared in the excited state and which decays with the rate gamma. In this case, what Purcell factor does is that it describes the acceleration of this emission. So, for example, if our organic dye in free space decays with a very, very low rate and it has a very long lifetime, by placing this quantum emitter close to another antenna, we modify the emission intensity and thus we modify the emission rates, gamma, the rates of this process of decay from the excited to the ground state. And the extent to which we modify this emission rate is exactly the Purcell factor of the system, which is only described by the classical quantity, by the Green's tensor of the system, by the Green's tensor of the environment where we place this quantum emitter. So now a few words about density of states in general. Let's say we have a perfectly closed resonator, just something that I sketched here, surrounded by perfect metallic walls. Then the system has a spectrum of eigenstates, En, and these states have real valued frequencies, they can be normalized, they have infinite lifetime. And if we attempt to calculate density of states, local density of states in this case, then the resultant spectrum of local density of states will feature a series of delta function peaks, because the line width of every mode is 0, and if you simply count all the modes, remember that the definition of density of states is sum of delta peaks, omega minus omega n, sum over n. And so if the spectrum of a closed system is a function of discrete modes, then in the local density of states we're going to obtain a series of delta peaks. And then if we place a point dipole inside the system, somewhere in this system, and if this point dipole is resonant with at least one of the modes, with any of the modes of this system, then the Purcell factor is going to be infinite, because that happens because the radiation problem in the case of a closed resonator does not have a stationary solution. If the source is resonant with a particular eigenmode of the closed cavity, there is no stationary solution. This is what we also discussed on one of our first lectures, on lecture 2, when we were discussing radiation problem and eigenmodes of closed cavities. The radiation problem does not have stationary solution. The energy is going to oscillate back and forth infinitely long between the source and the cavity. And if you do not have stationary solution, that translates into infinite Purcell factor. And this is in agreement with the fact that density of states shows infinite values at resonances. However, if instead we consider an open cavity, for example, a cavity formed by semi-transparent walls, if we allow some leakage from the cavity to the environment, then what happens is that all the resonances of the system, they now are characterized by only finite lifetime, which means that frequencies become complex values. They acquire a finite negative imaginary part corresponding to finite lifetime of these modes. And if we plug that into Green's tensor, for example, into expansion of the Green's tensor over eigenmodes, we're going to see that local density of states now becomes finite, and instead of being a series of delta function peaks, it is a series of Lorentz peaks at resonant frequencies. And at every resonance, this quantity is going to give you only a finite value, consistent with the fact that the Purcell factor in the system will be only finite. So basically, the presence of radiative losses in the cavity transforms a series of sharp delta peaks into smooth spectrum that consists of a series of Lorentz peaks. And now finally I wanna derive the famous formula that describes the emission rate enhancements of a point dipole placed inside a single mode resonant cavity. So consider a cavity supporting a single mode with a relatively high Q factor, and let us place a dipole at a certain position inside the resonator, a dipole oscillating at frequency omega. And let us assume that the cavity hosts only a single eigenmode, at least a well-separated single mode whose line width is much smaller than the distance to other modes of the cavity. And let us assume this mode has a finite lifetime, tau. So now we can expand using the expansion of the Green's tensor of the system over eigenmodes. We can use this expression and write the Green's tensor in the following way, where E is our eigenmode and omega naught tilde is the complex frequency of the mode, which combines the resonant frequency and the lifetime of the mode. And we plug that into expansion of the Green's tensor. And now, having Green's tensor, we can, in principle, calculate the density of states at any frequency, and thus we can calculate the Purcell factor. So let us plug that into the expression for the Purcell factor. And if we do this, and if we keep only the leading term in the denominator of the expression, we obtain the following very, very simple expression, which contains the Q factor of the resonator, which is Q is omega naught divided by 2 gamma. This is the quality factor of our single mode cavity. Then we have the wave number or wavelength, whichever you like, and we also have this combination, which we already had before in some of our equations today. And this is projection of the local electric fields of the modes onto the unit vector that describes the dipole polarization. And this is, in principle, a measure of how well the eigenmode of the cavity overlaps with the dipole. If, for example, the dipole is placed in the part of the cavity where electric field is 0, then this dot product is also 0, and the dipole does not interact with the cavity at all, and the Purcell factor will be 0. There is no interaction between the dipole, the source, and the fields. And this is what I try to emphasize when I explain to you how local density of states differs from total density of states. Total density of states doesn't care about this projection. It only counts the modes of the system globally. But local density of states cares about how much field you have here in the current space of the cavity, at the current position of the cavity. And so we need to calculate this dot product between the electric fields of the cavity and the direction of the dipole. Now we can do one final step. And by the way, I forgot to mention that this is calculated for the resonant situation. Thus, the frequency of the dipole, omega, equals the resonant frequency of the cavity. So the dipole is on resonance with the cavity mode. We didn't have to assume this. The expression would have been slightly more complicated. There would be a Lorentzian term in the denominator, but this leads to the simplest results that is practically very common. And so one final step, we introduce the following definition. We assign the inverse of this dot product to the so-called mode volume, V. So the mode volume describes how well the cavity mode, the cavity eigenmode, is localized to, physically. So V describes the modes, the volume in space, inside which the eigenmode is roughly contained. And finally, if you use this notation, V, this combination of eigenmodes and dipole polarization, we obtain this following very elegant formula, which was first derived by Purcell in his paper more than half a century ago, and it is one of the most widely used formulae in nanophotonics that describes emission rate, enhancements, and inhibition and general modification by a lot of resonant structures. And here I tried to illustrate by pictures from this nice paper how exactly this process happens, how density of states, how change in local density of states in a resonator affects spontaneous emission. And this case just illustrates various cavities, various high-Q nanocavities that can be used in order to modify the spontaneous emission rate and emission intensity of dipole sources. And this is the simplest type of cavity, the Fabry-Perot cavity, that is formed simply by two parallel mirrors, and the cavity mode is confined in the space between these two mirrors in the form of a standing wave. And we'll be talking about some of these types of the cavities next term when we specifically talk about resonances and eigenmodes and quasi-normal modes of cavities. So this is the subject of the next term, but now I just want to give you an overview of different types of cavities and show how they can affect local density of states and emission rates. And then we can have some microdisc cavities, DBR cavities formed by Bragg reflectors, and we already had Bragg reflectors a few weeks ago on the lecture about photonic crystals. Each half of this cavity is just a one-dimensional dielectric photonic crystal, which acts as a mirror, and in the space between these two DBR mirrors, we have a well-contained cavity mode. And then we can have different kinds of plasmonic cavities, and roughly speaking, plasmonic cavities are nanoantennas that are resonant because of bulk oscillations of electrons that are contained by the metallic parts of the antenna. And so what exactly happens with the local density of states when we place a point dipole in a resonator? So this is a point dipole, a certain quantum emitter in free space, and it feels, according to the Fermi golden rule, it feels the density of states, electromagnetic density of states of the surrounding space. And the rate of the transition from the excited to the ground state is determined by this local density of states of the surrounding environment. And then we put this dipole in a cavity, in a Fabry-Perot cavity, plasmonic nanocavity, any type of cavity. And placing the dipole changes the local density of states inside. Classically, you can look at this you can understand this by looking at the Green's tensor and seeing that the Green's tensor changes, imaginary part of the Green's tensor changes inside the cavity, and that affects the local density of states. And change in local density of states in turn changes the rate of the spontaneous transition from the excited to the ground state. So this is, in short, how Purcell factor works in different cavities, and this is an explanation how it works on the language of local density of states and the green standard. So congratulations, guys, folks. This concludes the first parts of our course. Now we finished the radiation section of our course, and we finished first 4 sections. We have finished the fundamentals, the plane waves, the waveguides, and radiation. And next up is scattering. Scattering, resonances, quasi-normal modes, and so on and so forth. We're going to have a very, very interesting trip next term. But this is all for now. So next week I'm going to give you just one lecture on scattering, because the schedule of the course is a bit uneven, and I had to place one lecture on scattering in the fall term. So that's going to be a very introductory lecture about scattering problem in general and the scattering matrix. And actually, we're not going to talk about resonances at all next week. So this should be a good head start for you into scattering. And then 2 weeks from now, I'll be ready to take exam. And official dates for the exams for this program, if I remember correctly, is somewhere in January. I think this examination week starts around 15th of January and goes on for 1 week. But if you're ready, feel free to contact me, and we can meet here on Wednesday this time, and you can present your question. I will be happy to. Georgi, you don't have to do this, but if you want to, I will be happy to chat with you as well. So that's it. See you next week, and be ready for the exam whenever you want to. See you next time. Bye.